Hello, welcome back to the Hog Pit. Today we're in the workshop. Just thought I'd give you a rundown of the machines and materials that I use. The machine that I use most is a CNC router. The particular model that you can see in front of you here is a Stepcraft D840, which means it can route out panels that are 840mm by 600mm and about 150mm deep. I've also gone to the luxury of getting a vacuum table, so I can just throw some perspex on there and start the side blower, and it just sticks down and it saves an awful lot of time with clamping, and it's really solid in there. But that was quite a luxury expense, but I didn't always start on this machine. I started on this machine, which was a lot cheaper, and you can get them off Amazon for under £200 now. They're about as functional as mine in terms of what they can do and route out panels using the curd, but the big difference is obviously not only the size, is the accuracy. This particular machine doesn't quote any accuracy figures, which rings alarm bells, whereas this machine has a lot of specs to it. And it specifies an accuracy of about 1 micron in terms of the stepper motors, but that's only half of the story. The figure you've really got to look at is repeatability, and the repeatability of this machine is about 0.04mm. What that means is that if you move the cutting tool and then move it back to a place, it will return to within 0.04mm of where it was before, and that's key because these heads move around an awful lot when you're cutting out panels, and you've got to quite often do several passes, and having a repeatable path means that you don't get little steps, things like that, whereas this machine probably has a repeatability of 0.1mm at best. Now that's not much of a problem if you're just routing out plastic or wood panels with just holes in it, but I also produce a lot of my own PCBs, which require quite a high level of accuracy. Whilst I have produced them on this machine, it was a challenge, to say the least, whereas this machine has a lot more features to it and makes it a lot more easier. This machine is known as a moving gantry router, in that the gantry that supports the machine tool moves forwards and backwards. The machine tool also moves left and right on the gantry, and then up and down. So this is a 3-axis machine. So you can see from this angle there are 2 stepper motors here and here. They drive the y-axis, which moves this gantry forwards and backwards in the y direction as it's oriented. You can see here that the stepper motors drive a big lead screw, and in there there's a ball nut that this gantry then moves on the rails. The x-axis moves in pretty much the same way. The stepper motor's at the far end, and the y-axis, so there's a stepper motor and drives this lead screw, which moves the machine tool up and down. One of the reasons why I picked this machine in particular was that you can change the machine tools out, saving space. I can use one machine bed and gantry with a reasonable level of precision for my project, but I could swap the machine tools out as I needed. I started with this tool, which is the HF500 spindle. It's a 500 watt 20,000 RPM spindle, and has got an ER11 collet to hold the machine tools, which I'll talk about in a second. But if I turn this quick release lever, I can pull the machine tool out, and I swap it over for this module as quickly as that. It's a laser engraver and cutter. It's only just over 4 watts in power, so you can get much more powerful lasers as standalone pieces of equipment that are out of CO2 tubes, and they're 40 watts or maybe even 60 watts. But this is an LED based laser. Its main advantage is that it's got a very small kerf or cutting width of just 0.1mm. Means that you don't get a lot of waste, and you can also engrave very fine detail onto whatever you are engraving. The laser itself also has an integrated extraction system, so it gets rid of all of the nasty smells, and to be honest, I've started using it to cut an awful lot as well, simply because it saves the mess of swarf and chips. It's just a lot nicer to deal with, although it does take a bit longer. Being only 4 watts, it's actually better on power than the 500 watt spindle, but that's not to say the spindle's redundant now. There's many applications for it, which I'm sure I'll talk through in future videos. So the vacuum table works by having lots and lots of these little holes, and they're all connected to channels underneath there that break out into 3 distinct zones, 1, 2 and 3. Through this manifold I can turn each zone on and off with a little gauge there to show the vacuum pressure, and the tube runs all the way underneath the bench to this side blower, which actually produces the vacuum. It's not as noisy as I thought it was going to be, but it's still got some noise to it. So when you produce the vacuum, it just sucks the part down onto the bed. This rubberized mat is quite important. Not only does it help with the grip and the friction, it also allows you to drill through or cut through up to about 0.5 of a millimetre. It's a sacrificial part. Without the rubber mat, you'd be milling straight into the bed, and this wasn't cheap, so rubber mat's important. So when I need to cut through more than half a millimetre, such as drilling or cutting out pockets from the acrylic, there's a technique I use where I use this piece of MDF. It's just a sacrificial piece, sometimes called a spoil board, and I can put it on here. Now there are some dowels that I put in the bed here. That means that when this gets on, there are some holes in the bottom, if I can find them, and then when it goes on, it sits down firmly and it can't move even without a vacuum. So then when I turn the vacuum on, because MDF is porous, if I put a piece of work on there, it will still stick to the MDF, although the clamping force is reduced. It depends on the size of the part, of course, but it's very useful for quickly throwing things on throughout it where I need to cut through. The other thing that I've done to this board is I've drilled in some dowels here as well, and what that allows me to do is to locate a piece of material in the same place every time. So if I need to lift it off to check, I can just slide it back into the same place every time without having to re-zero the machine. So let's look at the spindle a little bit more closely. It's got this button here, which when I press it, it locks the spindle, otherwise it's just free to turn. That button's important so that we can get a spanner onto the nut of the collet and undo it. What that allows us to do is to take the machine tool out. We extract the collet all of the way and the collet nuts. You can see the inside of this is not a perfectly straight hole. It's got a taper on it. It's very slight. You might struggle to see it. You can see from the collet that definitely isn't straight. Now the collets are returned in the nuts by a little ring in here, and to take them out can be a little bit fiddly. If you just pull them out, you'll damage the collet. What you've got to do is you've got to push it to one side and then ease it out of the groove like that. So it's this groove here that sits into the groove at the bottom of the nuts. So why do we use collets instead of a 3-jaw chuck? Well, the 3-jaw chuck's a fast way of changing machine tools. The problem with these machines is that they spin at such high speeds, 20,000 RPM or faster for some, that you need to make sure that the machine tool is centered perfectly in the spindle, and a 3-jaw chuck just doesn't give you that level of accuracy. So the way a collet works is you've got these fingers around the edge that are all segmented, and when this tapered part goes into the machine, and then you have the nut on top, when you screw the nut down, you force the collet further into the spindle, and what that does is it closes each of these fingers up so it clamps onto the machine tool. Now what that means is that we need one collet for every single size, because these fingers on the collet can only close up by a certain amount. Now most machine tools like this come on a 1/8 of an inch shaft, or 3.175 millimeters. So this is an 1/8 of an inch collet, and it's an ER11 collet. The ER11 describes the shape of the back around here and the nut and the interface on the spindle. So whilst this has a 2mm cutting bit, it's tapered onto a 1/8 of an inch shaft. Now what that means is that I can just take parts in and out of here without actually disassembling all of this all of the time. But what happens if I want to drill a 3mm hole? Well, I have a spare nut and I have a 3mm collet. So the hole in here is designed for a 3mm diameter tool or drill, and it just slides straight in and comes out. But the 3.175 just won't go in there, it's too big, which is why we then need to use the 3.175mm collet, or the 1/8 of an inch collet. Here's a quick selection of some of the machine tools that I use. For general cutting and rounding, this is a 2mm ball-nosed cutter. Don't know if it will focus on that. There it is. It's got a radiused end, and it has 2 flutes. So that's great for going through MDF, through cheap and cheerful. And when they blunt, you can just throw them away. They're cheap enough; they're not worth resharpening. For plastics, I use this, which is a single flute cutter, and again this happens to be a 2mm, but you can get them in different sizes. The point of the single flute cutter is that there's a lot more space in that flute to remove material. One of the biggest problems with acrylic is that the chips get stuck in the flute, and then it creates a lot of friction and then melts. So using a single flute cutter on acrylic is really important. I have a bog standard twist drill. This is a 3mm twist drill with a standard 118-degree tip. Nothing special about that. Just use them to drill holes. This is quite a large example. I normally go for smaller ones, but this is what's known as an end mill. So you can see it's flat at the bottom, and it has 2 flutes, and these flutes all the way up here are all cutting surfaces. So they're incredibly sharp on these edges, and it's an end mill because you cut on these ends. It's not designed to drill down. In fact, it won't do that because, as you may or may not be able to see, the cutting point doesn't come to a tip like a normal drill does. So there's a dead bit in the centre of the bit. So if you try to drill straight down with this, you'll tear the machine material up and make a mess of the tool as well. So there's special ways that you have with these end mills to plunge into material. You don't plunge into material as it's known. You either helix, so it goes round in a circle and it's moving, or you ramp, where it goes along and down at the same time. That's the end mill, but it's this outer cutting edge that we're looking for, so it's good for cutting the sides of pockets. The last tool that I have is a face mill. This has 3 cutting bits. It's quite simply for facing. I use it for facing off quite often the spoil boards when they get too damaged and they need to be refreshed, and it just sits in there and you just go in and it just cuts a wide area. So the last thing that I need to mention about the collet is that when you put your machine tool into the collet, that you don't over tighten it. So it slides in there and it's got a little bit of play. What I tend to do is I push the button here to lock my spindle. I'll do it finger tight, and then using the spanner, it only needs to be nipped up a little bit. You don't need to really tighten it up. If you do that, you'll damage the collet and it won't run true anymore. So a few of the things that I have around the workshop that I use an awful lot. So degreasants and cleanings. I use acetone and isopropyl alcohol a lot. The acetone's great for getting rid of grease, but you've got to be careful on plastics. It melts quite a lot of plastics, which is why I've got the isopropyl alcohol as well. Hot glue gun, more than just used for sticking things together. It's an excellent way to insulate parts. So if you've got live wires or connections and you want to insulate them, you just blob a bit of hot glue on it and bob's your uncle. Also use the Dremel quite a lot to do some fine detail work. I use this particular press as well if I need to do any fine drilling through of PCB holes if I've not done it on a CNC router. The Dremel, like the machine tool, uses a collet system for accuracy and centricity of the tool, given that it can spin at 30-odd thousand RPM. So the last thing to see in the workshop is my electronics bench. That's where I do all my electricery. I use a number of tools that I've found indispensable doing electronics. Having a decent selection of tweezers, both angled and straight, scalpel. This funky looking device is a deburring tool and is used for taking the sharp edges off of material that you've just cut. I've got a permanent marker here, side nose cutters, needle nose pliers, and two types of wire cutter used for different size wires, big and small. This here is a solder pump, so if I make a mistake, you can heat up the solder and suck it off. I've got a normal soldering iron here and a hot air workstation. I use that mostly to do surface mount devices, or where I need to heat up and use things like heat shrink to protect some of the cables. I also have copious amounts of super glue, which I tend to stick my fingers together, and then a big wall of bits and pieces, all sorts of components and wires. So moving inside, we've got two 3D printers. On the right hand side we've got the Creality CR3 Pro, which is a FDM printer, or fused deposition modelling printer. Uses ABS or PLA filament. And on the left hand side, in the wooden custom case, we've got a Elegoo Mars 2 Pro SLA printer, or stereolithographic printer. The CR3 Pro is what I use to produce the largest prints. It's got a print area of 220mm by 220mm by about 250mm off the top of my head. It can take longer than the SLA printer, but it can do much larger prints. It's also stronger in some ways and weaker in others. Depends how you lay the layers down. If you put load between the layers, you'll peel them apart a lot easier, but it can take a lot more load when it's in 90 degrees to the grain flow. I've customized this a bit. I did have a Raspberry Pi in here as a print server, and I would drive everything, but I've robbed that for another project. But what I have up here is a little Arduino driven temperature and relative humidity monitor. It's wired into a power supply and a relay down there, so if it gets too hot, it kills the power to the printer. It's just a bit of a safeguard in case we get thermal runaway on the base plate and stuff catches fire. It just gives me half a chance to get out alive. So I've got this enclosure mostly because when you do ABS printing, it can be quite sensitive to ambient temperature. The first ABS prints that I did warped a lot as they cooled at the bottom. Having this enclosure means that you don't get any drafts, and it also stays a lot warmer. With build plate at 110 degrees and the hot end at 230 degrees, it gets up to about 40 degrees in there and it remains pretty stable. The SLA printer is in this custom box. That's because it's really quite smelly. The modern resins are much better than the older ones, but even so, it's pretty nasty smell. It's quite toxic. So to that end, I've sealed it. I've also put an extractor fan in here, which isn't running at the moment, which then runs out of a hose through that window when I'm printing. It's also got red LEDs in the ceiling because the resin is UV sensitive. It cures under UV. So I put red LED lighting in here so that I can see what's going on. The window on the case is also a red acrylic, and is designed to keep UV light out of the enclosure when it's printing. So this works a little bit different in that you pour the resin into the bed here, and the bed then drops down, and a UV light or screen underneath there cures the resin one layer at a time, so it prints an entire layer at a time instead of fusing material as the hot end goes round. So it can be quite a lot faster than the FDM printer. Mostly this particular model can cure in about 2 to 3 seconds. The older models were more like 5 or 6. So this really does smash through the prints quite quickly. I found it quite good for buttons and knobs. Its biggest advantage over the FDM is its accuracy. This thing will produce prints down to the micron level. I mean, really fine detail on the prints, whereas on the FDM printer you can lose a lot of detail because you're restricted by the layer depth and the width of the output from the nozzle, and quite often you can lose a lot of the detail. The other bits of kit that I have with the FDA is I've got an ultrasonic cleaner, which is important for cleaning the prints off when they come out of the SLA printer. I use isopropyl alcohol in the ultrasonic cleaner. Also use gloves for handling. The resin's really nasty. You don't want to get it on your skin. It will irritate it really badly. So that wraps up this vid on the tools that I use. In the next vid I'll go through some of the software applications that I use to drive them. I'll see you there soon.